maybe we'll just get started. It's the last session before the fun demos and happy hour, so we'll try not to get in the way of that. So yeah, we were asked to give a little kind of just an overview from a more developer perspective on what OpenThread is. So I'll give a brief introduction on OpenThread, background. Abton will talk a little bit about how OpenThread is implemented. And then Gabe will also talk about how Eero leverages OpenThread in their products. So just high level, I'm sure everybody knows this, but what is OpenThread? OpenThread is an open source implementation of Thread. Next slide. And it is, as far as we can tell, basically the de facto implementation of Thread that's supported by the industry. So, one of the things that really drove Nest and Google to release OpenThread as an open source project was, number one, to accelerate the adoption of Thread in the marketplace. And as we've seen, I think OpenThread is doing a pretty good job of that, allowing organizations to take Thread in and integrate it into their product in a very quick way, but also because we believe, Thread is a mesh network, right? So the robustness of that network largely depends on the peers that it's communicating through, right? And so kind of the Thread group in general, like we're all in it together, right? If the neighboring device that we're communicating through isn't working well, then that reflects poorly on our device as well. And so we really want to be, working together, building a robust and performant mesh network. Next slide. So what we did in 2016 at Google I/O, we announced the OpenThread project. We hosted on GitHub. It is funded through a GitHub Enterprise account. So Google provides 100% of that funding. And that gives us access to, huge allocations of GitHub Actions, which are basically cloud instances that allow us to do a large amount of continuous integration and give us access to all of the other GitHub services without any limitation, right? GitHub discussions for community engagement. And, really OpenThread is, while it is funded by Google, we really strive for it to be a community effort, right? Where anyone can contribute code, anyone can submit a bug report, anyone can review code that's posted. All of the code that's posted goes through a pull review process that's in the public. We don't, Google, for example, we follow the same process that any other community contributor will follow. Next slide. OpenThread itself is licensed under the BSD3 license, which is here, but basically it's a very open and permissive license. And I will note that its copyright is also the OpenThread authors, so not copyright Google. So OpenThread authors is basically if you just went through the commit list and uniqueified the names, that would be the list of OpenThread authors. So this is kind of directly addressing one of the questions that was raised, that was mentioned in the past from not just Thread group members, but others looking at Thread is OpenThread owned by Google? It's really not. While we do host, fund the hosting on GitHub, while we do help maintain the project itself, anyone can take that code and can fork it, can do whatever they want with it, right? It's subject to this BSD3 license. Next slide. In addition to the code itself, we provide a number of tutorials, documentation, reference documentation for APIs. And so this is hosted on the Google developer site. But again, all of this documentation is also community contributed. So we have a public GitHub repo that, again, anyone can contribute to and review, where you can submit your own docs, right? If you have a how-to guide that you'd like to contribute to this site, you can write it in a markdown format, contribute it. We do have tech writers that are willing to help do the copy editing for you. So, if you're just an engineer and want to contribute something, but we will help with the actual copy editing and getting it into a format that looks nice on the dev portal. Next slide. And then this is just a listing of the silicon vendors that support OpenThread in their various development kits. This has grown over time, and it's practically every silicon vendor that's a Thread group member. Next slide. And OpenThread is currently shipping in a number of products. And the importance of this for me is that OpenThread is being used in a number of products in production today, right? So anybody that's using OpenThread gets to take advantage of all of the work that everybody else has done in the past to integrate OpenThread, to make it robust and make sure it works in a performant way, right? You get to leverage all of that, right? And so with that, I'll hand it off to Apton to talk more about OpenThread as it's implemented.
Thank you, Jonathan. Okay. So hi everybody, I try to be quick on this. So just a quick outline of the things that I want to cover. The first part is basically a quick overview of like what are the core and what are the public platform APIs. Then followed by different architectures that are provided or supported by OpenThread, RCP, NCP, SOC. Very briefly going over core modules and the layers that we have there, build systems and configs that we have, few slides on simulation and the different testing that they do. And then towards the end, maybe some less known features of OpenThread that I want to highlight and mention. Very quickly. So OpenThread, we have the OpenThread core, which is the main implementation. That's C++ 11 based, and it doesn't use any of the SCL or any other thing. We try to keep it as portable as possible. It expects that there is a set of platform APIs that the platform provides, and that's often things like device drivers or operating system related things. And the platform API is all C based, and there are C definitions. And they all start with OTPlat, the module name. And then on the other side, it provides a bunch of public APIs for the users of ThreadStack that wants to control and basically enable and do stuff with the ThreadStack. And again, the public is C-based. The public API is C-based. Next slide. Yeah, on the different architectures, so the simplest model of using it is basically SOC model. Well, the entire thing is running on the same chip. Basically, the OpenThread core and a stack is running the same chip, which is a 15.4 radio, and then application is running on it and controlling the device using the OpenThread APIs. The other model is where we have multiple chips, basically. We have a host and an NCP or RCP. In the first case, we have a host that's basically trying to control a network coprocessor. The network coprocessor is actually running the full OpenThread stack, and that's the one that actually has the radio. And then it provides a connection, or which we refer to as SPNL, to the host. Basically, it's a mechanism for the host to control and issue commands and basically mirror of the APIs that OpenThread provides. The other model is again multiple hosts. It's referred to as RCP, where at this time the OpenThread core is actually running on the host itself. And we basically treat the SOC or the radio is purely as a radio and just control it again through the SPNL, but through simple APIs like go to receive, go transmit, send this frame, and things like that. And in a sense, this is actually very similar to SOC instead of like the radio itself is actually running on a separate chip. Yeah, next slide, please. So very briefly, in OpenThread, the core part, we try to follow some sort of a layered architecture, which is somewhat similar to all the different networking architectures. I'll go very quickly over them. So if you can click now on one thing. So there are a bunch of common library stuff that things like timers and tasklets and data structures that do different type of processing. And they are shared across all and they're used by all. Then after that, next slide. After that, we have the MAC layer, and then the MAC itself is divided into different layers, including sub-MAC, and then some other components that do specific things like CSL transmission, data pole handling, and other things. And we have also a big module there, which is mesh forwarder. That's where all basically it's the glue that sits and does a lot of different works. And basically the send queue, message queue, the priority queue, all of those are sitting in that mesh forwarder layer. Then we have the IP, LoWPAN, UDP, TCP, socket notion, NetIF notion on top of it. And then after that, we will have the thread layer protocols, MLE, TMF, and then more specific functions like address resolving, key management, stuff like that. And here's where we have child table, router table, neighbor table maintained, and network data, of course. Then on top of it, we have mesh commissioning related stuff, the data set, operational data set, active, pending, data set manager, and notifier, and updater, and different things. And joiner commissioner codes also are sitting in this layer that are implemented. So there is the border router modules. So this is where things like determining the OMR prefix, checking if my Wi-Fi network or my infrastructure network has already a prefix, basically advertising and doing those sort of things. That's where that code basically sits. And then everything else I refer to it as utilities, things like SRP client, server, DNS resolver, DNS client, all those things are basically other things that are running on top of the IP and on top of the UDP and other things. So I think this is the full thing. Now, in general, the way OpenThread is built is that it's built as a library, and then you have a platform implementation that you link it with, along with an application layer that uses the OT APIs. In the OpenThread repo itself, there are two example apps that are provided. The first one is the CLI, which basically exposes all the OT APIs as command line interface commands. And there's an example of this, like the documentation on the side, and all the different commands are documented in under a README file. That's like what the format is, what the parameters is, and there are examples of what each of them do. And I want to say that to a good extent, they mirror all OT API. Whenever we add an OT API, there is a CLI command added along with it. And there is the NCP mode, which is what we mentioned. This is the SPNL interface that basically talks to the host. In terms of build systems and in general make files, the main thing that we recommend and use ourselves is the CMake and Ninja, and I can say it's significantly faster than AutoConf that we were using before. And BuildGN and Android MK files are also used, or we track there. And there is an AutoConf version, but we may deprecate, or it may be deprecated later on. At the high level, when you build OpenThread, there are three high-level configurations. You are either building an FTD, MTD, or the radio. Radio is the one that you would use for your RCP build. And then beyond those configurations, there are many other options to tune the network, enable or disable different features in OpenThread. So all the configurations are under source core config, and there are a bunch of different header files there. So, and each of them associated certain feature or certain functionality. And at the high level, a feature is like we have OpenThread config feature enabled to fully enable or disable a particular feature. And then there are further parameters to tune that specific feature that are defined below. And there are some guards that are added in the stack that, like, if you misuse the configuration, certain things, you get a build error, or if you use a renamed or removed the parameter, you will get a build error. It's better to fail hard in those cases to see that there is something bad. Some of these configurations and build flags, you can also control them or enable or disable them through some build switches. And there is, again, a documentation of, there is a CMake switch and AutoConf switch associated with that. So this is not full list. Basically, this is a subset of the previous set of configs. And this is more towards high-level features, like I want to enable joiner functionality, or I want to enable commissioner functionality, or things like that. The recommended or better model that, like, for product or project is basically have a custom project-specific configuration, and then there is a mechanism to say, I want to use this configuration header for my build, and then that would be the one that would be clear what is being used for that product or platform. One quick thing on the logging side. So we have we provide a lot of different logging and different levels in OpenThread. So there is debug, info, note, and these are the ones that are for debugging, and they provide different level of information depending on the capability of the device. Debug is often very verbose. It's only for custom builds that you want, but info and note are more useful even for the in-field debugging. They can be set by build config at the build time, but there is also a feature that you can dynamically set the log level at the runtime, and you can change it if you want. That's very useful for testing. And then the log output itself can go to very different. There's a lot of configuration of where do you want the log to go, to platform layer or to your app layer or to different place, different formats. And the log line itself is very configurable, what you want to include in it, append uptime, name of the module, stuff like that. Next slide. In terms of simulation, so in the OpenThread repo itself, we have one platform implementation, which is referred to as simulation. And this basically emulates all the Plat API behaviors. for example, for the radio, what it does is actually like it emulates the radio API behavior, what you expect it to have. And there are two main modes of operation for this simulation platform. There is a virtual time mode where basically it's the job of the test the script itself to manage the flow of time. The good thing about it is that you can run tests very quickly, but it's more complex to do because you need a separate process to basically dispatch the events between different things. And your test the script itself should say, move time ahead and go to this time and this thing. There is another mode, which is actually real-time mode. This basically, the device itself manages the time. However, we can still run it with a speed up. We can run it 10 times the speed or 5 times the speed. So things can be run much more quickly with that mode. It's much easier to use, and they are used for different type of tests or test the scripts. There are different tests. These are just a subset of different test environment that we have. Unit tests that are used for different modules. There are a bunch of different test scripts that we refer to as thread set, but there are more that there are tests that are covered the same as thread set, but there are some additional ones. They use the virtual time, so they run very fast. They're all in Python, and there is a flavor of them that they do packet capture and packet verification as well. That's like if the packet is formed correctly over there, or when it's sent. There is another test framework which uses a real-time simulator with a speed up that's easier to start writing tests on, and that covers NCP and CLI mode. And there is OTNS, which is in Go language, and it has actually a nice web-based interface to build topologies and try out different things with this.
That's using virtual time.
I believe so. I think so. Yeah. I think that it's virtual time. Yes. If again the Go process has something that it manages the different things. I don't know if it has a real time. I think it's only virtual time. Yeah.
There was also on previous slides. I think it was virtual or real where it's kind of mixed up.
Maybe that's the same. Yeah, that's correct. That's the wrong leader. Yeah. That's wrong. So, as Jonathan said, we run a lot of GitHub actions and a lot of different tests and different checks that are run in every PR and on main every day, basically before they are merged. There are formatting checks, version checks, makefile checks, and stuff like that. We run a size report on every pull request, which shows how much code size, RAM size is impacted by the change that the pull request that is submitted. And it tracks different things, one changes, two changes, and different libraries. What's the basically impact of them? Different builds to cover that the stack is built like ARM GCC, different versions, Clang, 64-bit, 32-bit, 16-bit, and a lot of simulations that I think we covered, and some of them, some more basically. So, I'm reaching towards the end. I want to just highlight 2 or 3, maybe less known features of OpenThread. One of the ones that I encourage people to consider is this feature called History Tracker. This basically intended for more capable devices that don't have, basically in the sense that they have RAM and border router style that you're not restricted by memory. It basically tracks the history of different items or events on the device, and it's useful for debugging and knowing what's really happened in your network. It tracks things up to millisecond accuracy and up to 49 days. After 49 days, it still remembers them, but it says 49 days ago, this thing happened. So I don't know what happened. Basically, it doesn't track the time exactly. It tracks of whenever you're in your network, the device's role change, you get detached, attached, partition ID changes. It keeps track of all the different neighbors, when they are added, when they are removed, what mode they were on, what was the average RSSI to this neighbor, addresses, multicast, unicast addresses. One thing that's very useful is network data entries. No matter, basically, anytime some prefix is added, by whom it's added to the network, or external routes that are added or removed, by whom they are added to the network. And we're hoping to add more on this as well. And also there is a mode to enable to capture a set of last X received messages, transmitted or sent messages. And again, it tracks a lot of things, like who received it, from which neighbor you received it, on which radio you received it. All this stuff is tracked and can be basically later on. The other features that I just want to quickly mention, we have a feature called channel monitor. Basically, the idea of this module is that it sits in the background and it slowly takes sample on every channel to try to build the view of how crowded or how busy different channels are. it takes samples very slowly, and it just picks one RSSI sample every like minute or so in that order. And the idea is that it averages it out over a long period of time, days or weeks worth of data. Basically, it's averaged out. And we found that it actually, in a very good way, detects how busy the channels are. It actually detects the Wi-Fi's that are being used in the environment, and over the long term, it's actually quite good at tracking the busyness. The other one that's related to this is the channel manager. Basically, the idea of the channel manager is like, the first part is it just provides an API for the user to come and says, I want to change the thread channel on all nodes, basically every node in my network to channel 10, like go switch it. And underneath it basically tries to manage it, does this with the pending data set. And if it fails, it tries again and tries to do basically what is asked. But then it has also a mode that you can ask it, go select a good channel on your own. And it only works if the channel monitor is there, and it goes and says, like, have we been running long enough? Do we have enough data? Let me pick the channel for you. And there is also a third mode where you can automate it and says, every so often go check if you can switch the channel or not. So it can actually does it on its own. Another quick thing is the jam detector, which is actually detects whether the device is being jammed. Yep, I think that's.
Cool. I was going to kind of give a quick overview of a little bit of how we integrate OpenThread into Eero products and some of the lessons learned, and this doesn't fit there. And show you a couple of our tools and see if there are any questions. Cool. And I'm going to stay out of present mode if that's okay, because I'm going to flip back and forth between some tabs. So hopefully it's big enough for everyone. Cool. Well, Eero is a Wi-Fi router, first and foremost. Pretty simple little white box that doesn't have much input or output other than the fact that everything in your house talks through it. We have a common Linux OS across all of our products. Different products have different kernel versions or may have different hardware features, but they all build from the same OS. We, of course, have cloud control, which is pretty standard these days, but we also have local control mechanisms between each Eero and between mobile apps and the Eero device. So we have kind of trusted comms in all of those directions, which allow us to sync configuration between Eeros, do really rapid things like Wi-Fi channel changes coordinated locally on the network. We update our software regularly, which the security people like. And we have OTBR, OpenThread Border Router, integrated on 6 certified products today with more products coming. It's pretty exciting. Unless we change something drastic around hardware, it's a one-line change to add a product today, which is pretty cool. So we can pretty rapidly turn the feature on for new devices. I'm going to skip over these really quickly because I think Jonathan and Abson did a really great job of describing what OpenThread is as a project and as a piece of software. I think one thing that I didn't hear in there was the vendor examples. So I think all of the vendors, at least most of the vendors, have examples in the OpenThread GitHub account in their own projects that give you a pretty basic representation of OpenThread on that platform. And so if you are new to Thread, which I don't think anyone here is, and you just want to, you want to go to your CEO and show them Thread running on a Scilabs board, this is the place to start. And every vendor kind of has examples. They're very easy to use. They're very easy to build. They all have reference devices. Each vendor has their own kind of opinion on how to use the OpenThread, their OpenThread example. And so the vendor is your partner, and you have to work with them and work with your own teams to decide how you want to integrate their software. I have a very strong opinion about this, but every team is different, and we'll get into that a little bit. So along those lines, every vendor has their own IDE or SDK, whatever they'll call it. I'm showing Simplicity Studio here because they have lots of images of Simplicity Studio on Google. And these tools make it easier for you to configure things. So, you know, Abthan just showed a bunch of compile flags and build flags. A lot of these tools will make those into WYSIWYG checkboxes where you say like, I want coax, and you check a box and it includes a bunch of software to let you do coax. It also has a lot of other features that have nothing to do with OpenThread. So, you know, if you want to make the Scilab's Gecko bootloader do some crazy thing, or if you want to control an LED on your board, you're not going to see a lot of support or any support for that in OpenThread. So really the vendor tools are the place to look. And so depending on your product, depending on your level of comfort, your vendor will probably tell you to start with these tools. And as you get more comfortable, you'll decide if they work for you or not. I don't think that I heard much on the OpenThread border router project on top of OpenThread. But the OTBR project is a separate GitHub project maintained by Google, or mostly by Google. And it is kind of a fully featured, fully working example of a border router. It is the thing that you should build if you want to play with any border router feature as they're being developed. It's almost shippable, but it's not meant to be shipped as a product on its own. So it gives a really good example that you then integrate into whatever the actual mission mode of your product is, whether it's a lighting controller or a Wi-Fi router. And so you shouldn't expect to be able to take OTBR and just hand it to customers, but it's actually pretty close. And I'll show you an example of how close it actually is. I kind of have some notes on sort of crawling and then walking in terms of how I approached moving our products to OpenThread. To me, there's sort of a separation between what I'd call board support or the MCU or the radio, where you have to figure out, you know, again, with the help of your vendor and their FAEs, how are you going to get a 15.4 radio with the OpenThread protocol running? And so, for example, in some of our products, that was working with Scilabs to figure out how we could do field updates from Scilabs Thread or from Scilabs Bluetooth into an OpenThread RCP and make sure that we can safely update the part in the field without bricking it. And I spent a lot of time on that before ever touching anything that was actually like Thread protocol. It was just, how do I get Thread running on the part? So that's where I would start if you kind of think of your hardware layers. And then of course it's, you know, form a network, get familiar with like using the CLI, like the very, very basics of using the tools. And then using the OTBR on a Raspberry Pi, you know, it seems pretty common that people will play with features before they try to make them work in their own product, because it is a known platform. If you go onto a GitHub discussion and tell Jonathan something doesn't work, it's much easier for him to support you if it's on a platform that he understands and can build on his desk versus your custom platform that you've done some crazy configuration on. Working up from there, you know, you need to integrate this into your build system. I'll show you how it integrates into our build system. You need to think about things like PTA coax. You know, how's this thing going to get configured? All of those things. But the CLIs, you know, that Abthan showed a bit of, as well as things like the dbus APIs that OpenThread expose, make it pretty dang easy to configure this thing. So once you know what you need to configure, which is not a lot of stuff, it's pretty quick. So yeah, then there's tweaking, and again, I'll show an example of this in a second, but you're going to have things that you need to customize for your platform. In our case, it wasn't a lot, but it was things like, where does the OpenThread settings file live? How does logging work, which we worked on last week? And the OpenThread team, super responsive to, you know, adding build time flags, helping you kind of make that work for your system. It's also really helpful if you have some kind of cloud or some kind of means to turn things on remotely or turn things off remotely, because invariably customers are going to have weird situations, and that gets us out of jail a lot of the time. I'm going to stop there for a second and switch tabs, but you know, we were in a board meeting, I think yesterday, and I think people thought that I was joking when I said that once a feature is in OpenThread, I can get it to our field in 6 to 8 weeks, I think was what I quoted. And our philosophy has been to stick as close to upstream as possible, so much so that this is actually the Yocto build recipe for OpenThread border router into all Eero products. And it builds from the OpenThread OTBR main branch with a pinned commit, and that's it. Like we're not forking, we're not doing our own crazy stuff. And then we, again, as Apton and Jonathan kind of walked through, we have a bunch of configurations that are unique to our platform, or some of them are. And that's pretty much it. It's pretty simple. Where it gets a little bit more complicated is how do you start the border router process? How do you configure it? Things like that. But getting the software into our system, it's literally what you see right here. One thing that I wanted to show, because I built it and I thought it was kind of cool. So we build an RCP image. It happens to be for a Scilabs radio in this case. At Eero, the history was that RCP image was built by hand on an engineer's local machine. And that was the case for 5 years. Anytime we wanted to change that RCP image, it had to be built and cryptographically signed on an engineer's desk. Not great. So we've since moved that into some automated build tooling where any merge to a forked repo in this case to mainline, it kicks off a build, it signs that build, and we end up with an RCP image kind of that is signed and encrypted, matching what Scilabs expects from their bootloader. Happy to share some of that scripting and information on that if anyone has use. The next little bit quickly gets into testing. So the OpenThread and OTBR projects are pretty dang stable. Jonathan mentioned GitHub Actions. There's a ton of CI. Like our engineering team was impressed when I forked the repo and they saw all of the CI that started breaking because I forked it. It's very well tested. So when I want to try a new commit of OpenThread and OTBR, the first thing I do is some very basic hand sanity of like, can I ping from one end device to another on our network? Can I ping from a Wi-Fi client to an end device? Do I see, the mesh cop services being published that we expect? And then like, does RF generally work? Can I scan and see other thread networks? Because I have like a dozen of them in my house. If these things fail, typically it means that one of our radio vendors is not ready for something that is happening in OpenThread, or something wasn't rebased somewhere. It's very, very rare that I've seen something fundamentally broken in upstream OpenThread. It's extremely stable. In addition to that, we've built out some automated testing that kind of runs through the equivalent of that sanity, but on a slightly larger scale. So these are multiple Eeros in shield boxes with Raspberry Pis that have thread devices hanging off of them. And it goes through, can I see the thread network? Is it configured correctly? Can I ping from one thread device to the other? Can I ping across the trail? Like it's making sure that we didn't do anything stupid. And almost always it's our fault, not the OpenThread teams. And so, a quick example, this is what our UI for this tool looks like. And in this test, we failed to ping from one thread client to another. I think that this was actually flakiness in the test that we then went and improved, but just to kind of give a sense of how we make sure that we have some quality. A plug for GitHub discussions, so I don't think Jonathan did. Do not use the Google group. Do not Slack Jonathan. That is reserved for me. And use the GitHub discussions. I also strongly recommend, personally, I like to go and search open pull requests, closed pull requests, issues in GitHub and the Google group, because I don't know, 20% of the time someone has asked a question or has pasted some piece of text that probably gets close to the answer of what I need. So you can find a lot of historical information if you search. People never search. So Jonathan's a very nice person though. I guess, yeah, to wrap up, one thing that has kind of exploded brains at Amazon is, they say to me, what is the OpenThread release that we should be using in our product? And I say, there's no such thing. We have to pick a moment in time and assume that we will pick another moment in time in the future. And so my, personal philosophy or what we do at Eero is, we have a release, let's say every 8 weeks. Somewhere in our release process, I will go and bump the commit. I'll ask Jonathan if there's anything interesting coming. I'll look at what's recently been closed in terms of PRs. And before we lock down our release, I'll move to a new commit and go through all of our testing. There may be a tagging or release strategy in the future, but my message is stay as close to top of tree as you can, because it just makes it easier to get support from the community. And what I've noticed is if we wait 2 or 3 releases, things diverge, and it's just annoying to move ourselves up. Yeah, so talk to the community. It's a really strong community. Talk to your vendor, make your vendor do work for you. They don't like to. And yeah, I don't know, any questions for me? Oh, Christian.
Yeah, how do you handle certification with OpenThread if you're using the GitHub?
Yeah, we pay attention to what's going in, and if there's something that looks like it's going to fundamentally, require research, then we'd stop and think about it. But I haven't seen changes that necessitate that.
My point is more from the perspective of you're changing the software.
Yeah.
It should be recertified.
That we should talk to Tom, because my understanding is it's really based on what's changing functionally, not simply the fact that you're updating your software. Yeah. Nathan?
Yeah, I was going to say the lack of tag, I wonder if that's something we should consider.
I guess I would be curious from the community what would be worth tagging. Like, commits in a way are tags.
From our perspective, we would like to tag certified versions.
And I think that you do already, because if I email you and I say I'm using yesterday's commit of OpenThread, you're going to say, well, we only support up to 4 months ago, and I say, well, that doesn't work for me. And so I think that's where there's some negotiation with each vendor. Yeah.
I mean, doesn't the harness have an associated with that? Like, you could align your harness to.
I think that's what the vendors do. Yeah. It's too slow.
Yeah.
Cool. Thanks, everybody. If you have more questions, let me know.